Good morning, students. Today I am going to teach you the second chapter, Basic Sequential Circuits. So, contents: relevance of asynchronous inputs to flip-flops, lays around problem and remedies, master-slave flip-flop. As you studied in the previous class about the two types of flip-flops, which are SR and JK flip-flop. So, we studied in different cases, like when S is equal to 0, R is equal to 0, the Q and Q bar was in no change state. And when S is equal to 0, R is equal to 1, Q was 0 and Q bar was 1, that is reset state. When S is equal to 1 and R is equal to 0, Q was 1 and Q bar was 0, which is set state. And when S is equal to 1 and R is equal to 1, that was a invalid state or intermediate state. So this problem was solved by using JK flip-flop, where when J was 1 and K was 1, both Q and Q bar were in the toggling state. So in order to solve the invalid state condition, we use the JK flip-flop, which shown the value, that is toggling state. Where J and K are the inputs, clock is also one input because both are synchronous inputs. So the other two PRE, which is preset, and CLR, clear. These two are known as asynchronous inputs. So it is also having two outputs, that is one is Q and Q bar. As you studied in the previous class, both SR and JK flip-flops were synchronous inputs, means they were clock dependent. Whatever may be the flip-flop, their status or their action or their effect were totally dependent upon the clock input, and therefore they were called as synchronous flip-flop. Now we are going to study in this unit asynchronous inputs. What are these asynchronous inputs? Here we are going to use two asynchronous inputs, which are namely preset and clear. So what will they do? They are totally independent of what? So they are totally independent of synchronous inputs and clock input. So let us study the truth table. Here inputs preset, clear, both are asynchronous inputs, clock input, and two more are J and K inputs. And there are two outputs, which is Q and Q bar. So first case, when preset is low and clear is high, that is preset is in 0 value and CLR, that is clear, is in high value, that is 1. So irrelevant of the inputs, clock, J and K, that is irrelevant means they may be 0 or 1, don't care condition. What happens to the output? When Q is equal, when preset low and clear is high, we get Q is equal to 1, that is 1 state, and Q bar is equal to low, that is 0 state. Q will be high and Q bar will be low, that is Q is 1 and Q bar is 0, and this action or this state is known as asynchronous set. Second case, when preset is high and clear is low, what happens? Irrelevant of the inputs J, K and clock, so Q will be compulsorily low and Q bar will be compulsorily high, that is Q is 0 and Q bar is 1, and this is known as asynchronous reset. Next, third case, when preset is low and clear is also low, means both are in 0 state. So irrelevant of the clock J and K. So what we are going to observe? We are going to observe both Q and Q bar will be in high state. High state means logic 1 or 1 state. So both will be high, and this is known as prohibition state, means both Q is also 1 and Q bar will also be 1. Actually this state must be avoided. So remaining cases are acting like normal JK flip-flop. So fourth case, when preset is high and clear is high, what happens on the application of the clock pulse? On the application of the clock pulse, if J was 0 and K is equal to 0, so Q and Q bar will be as it is. They are going to be in no change state or old state or previous state. So Q will be Q and Q bar will be Q bar. So fifth case, when preset is high and clear is also high. On the application of the clock pulse, when J is equal to high, that is 1, and K is equal to low, that is 0, so Q bar will be compulsorily high and Q will be compulsorily high and Q bar will be compulsorily low. So whenever J is high, Q is also high. So this state is known as set state. Since it is dependent upon the clock pulse, so this state is named as synchronous set state. So next, sixth case, when preset is also 1, that is high, and clear is also high, that is 1. On the application of the clock pulse, both if J is equal to low, that is 0 state, and K is equal to high, that is 1 state, what happens to the output? As you studied in the previous class, Q will be low and Q bar will be high. That is, this is known as reset state or synchronous reset state. So last case, seventh case, when preset was 1, that is high, and clear is also 1, that is high. On the application of the clock pulse, if both J is equal to 1 and K is equal to 1, both are in high state, what happens to the output? Q and Q bar are going to interchange the value, and this is known as toggle state. Means they are going to change their state, opposite state. So this is known as toggle state, and this is a brief description about the truth table of asynchronous inputs to the flip-flops. So first case, when Q and Q bar H and L, that is known as asynchronous set. L and H, that is asynchronous reset. High Q and Q bar, that is known as prohibition state. Q naught and Q naught bar, that is hold state or previous state. And Q and Q bar H and L, that is synchronous set state. Q and Q bar, that is L and H, that is synchronous reset state. And last case is toggle state. So this is a brief description about the asynchronous inputs to the flip-flops. So main use of asynchronous inputs are they are totally independent of the synchronous inputs, and clock means they can be used to set or reset the flip-flop at any time regardless of the conditions of the other inputs. So this second concept, that is race around problem and remedies. So what do you mean by race around problem? Toggling of the JK flip-flop is more than once in clock period when both J and K inputs are high is called race around condition. So this is known as race around problem or race around condition. So what are the steps to avoid racing around current condition in JK flip-flop? So one of the way you study means let us assume that when J is equal to 1 and K is equal to 1, what happens? Q will be 0. So when the clock is applied, the upper gate passes the set pulse and Q becomes 1. So this occurs in a duration that is T is equal to TP nanoseconds, or TP is equal to propagation delay. Now the next situation, when J is equal to 1 and K is equal to 1 and Q is also 1. What happens if the clock is still in on condition? The lower gate passes the reset pulse and Q becomes 0. Usually clocks have a time period of few microseconds compared to TP of few nanoseconds. It can be seen that period of a clock pulse is equivalent to hundreds of propagation delays. So when J is equal to 1, K is equal to 1, the output of JK flip-flop will toggle continuously until the clock pulse becomes 0. The final result of this toggling action master-slave flip-flop. So one of the means or one of the method to avoid racing around problem is, as you see in the first point, if the clock is in on state or in high state, the time is less than the propagation delay of the flip-flop, then racing can be avoided. This can be done by making use of edge triggering rather than level triggering. So next, second case, if the flip-flop is made to toggle over one clock period, then racing can be avoided. So this introduced the concept of master-slave flip-flop. So third concept, that is master-slave flip-flop. So you can also call it as MS flip-flop. Okay, M refers to master and S refers to slave. So it was developed mainly to avoid the racing around problem which was faced in clocked flip-flops. So this was achieved by introducing a time delay equal to the width of one clock pulse for its output to change the state. So master-slave flip-flop was also called as pulse-triggered flip-flop. So it contains two flip-flops. One is master flip-flop and second one is slave flip-flop. The control inputs are applied to the master flip-flop. So when clock is equal to 1, the levels on the clock control inputs are used to determine the output of the master. So when clock is equal to 0, the state of the master is transferred to the slave. So whose outputs are Q and Q bar. So we shall study in briefly in the truth table. So thus the actual outputs of the flip-flops, which are nothing but Q and Q bar, will change only on the application of the clock when it goes low. So this is the logic circuit of master-slave flip-flop. Similar to the JK flip-flop, it is having one set of master flip-flop is having JK inputs, clock input, Q and Q bar, and second set of flip-flop, that is slave input, is also having two inputs, that is J and K, Q and Q bar. Clock of slave flip-flop. Can you see that NOT gate? Yes, NOT gate indicates the clock input inverted or inverted clock input. So it is indicated by CLK bar. So next, this is the implementation of JK master slave flip-flop using NAND gates. Similar to the JK flip-flop also, it is having 4 sets of NAND gate. Here since you are going to combine master and slave flip-flop, totally you are having 8 NAND gates and 1 NOT gate. So first NAND gate input is having 3 sets of inputs. One is from J, one is from clock, and feedback line from Q bar of slave flip-flop. Next, second one of NAND gate is having 3 inputs. One is from Q, one is from clock, and another one was feedback line from Q. Okay, so J, clock and Q bar line. Next, K, clock and Q line. So this is the arrangement of master and slave flip-flop by making use of only NAND gate. So you can see one small difference is that you are going to have one NOT gate because you are going to send inverted clock input to the slave flip-flop. So let us briefly study the cases. So what happens in the 4 cases on the application of the clock pulse? As you know, irrelevant of the clock pulse, whether J is equal to 0, K is equal to 0, the outputs remain as it is. So when J, on the application of the clock pulse, when J is equal to 0, K is equal to 0, Q and Q bar will be as it is because the flip-flop is disabled, and this state is known as unchanged state or no change state or previous state. Next, when J is equal to 0 and K is equal to 1, so what happens? The master resets the slave flip-flop to come under reset condition. So output of slave, that is Q, becomes 0 and Q bar will be 1. So this is known as reset state. So next case, if J is equal to 1 and K is equal to 0, what happens to the master flip-flop? It will automatically sets. So on the application of the clock pulse, the master flip-flop sets. So further, when the clock is equal to 0, this forces the slave to set. So the output of Q will be 1 and Q bar will be 0, and this is known as set state. Last case, when J is equal to 1 and K is equal to 1. So master toggles when on the application of the clock pulse. Further, when clock is equal to 0, this forces the slave to toggle. So master also toggles, slave also toggles, or when master sets, slave also sets, or from whether master resets or slave will also reset. So the slave follows the master. So this is the brief description about the truth table of master slave flip-flop. Next, timing diagram of JK master slave flip-flop. As you have seen, since it is a clock dependent circuit, you are going to have clock signal. Next, J input, K input and Q output. As you see, when both J and K are 0, no change state. When J is high, Q is 0, Q will be high. When J is 0, K is high, Q will be 0. And both when J is equal to 1 and K is equal to 1, it toggles. So similar to the JK flip-flop. So here main condition is master follows data to the output on the falling edge of the clock signal. So this makes the master slave JK flip-flop a synchronous device as it only passes the data with the timing of the clock signal. So today you studied about relevance of asynchronous inputs to flip-flop. Second one was raising around problem and the steps to avoid the raising around condition. And third was master slave flip-flop. So these three concepts are being studied today. So these are the basic importance of today's session. Thank you.